Welcome back to the Engineering Systems Explainer series. Let's pick right back up with our availability patterns and our fictional food delivery app, FoodDash. In our last explainer, we successfully eliminated our single point of failure using redundancy and replication. So, instead of just one database, FoodDash now has two, a primary database handling all the live production traffic and a secondary database continuously receiving replicated data. It kind of looks like we've solved the problem, right? Well, have we? Okay. Let's really dive into this. Imagine the primary database suddenly crashes. Sure, the backup database is sitting right there. It's fully replicated, totally synchronized, and completely ready to jump in. But here's the massive, million-dollar question. With thousands of hungry customers waiting for their food, how does the system actually know the primary failed? That shiny new backup is literally useless if nobody knows when to switch over to it. And that brings us to our first core concept, health checks. Think of a health check as a simple, automated digital pulse. The system is continuously asking, hey, are you still alive? Every few seconds, FoodDash sends this tiny request in the background directly to the primary database. The database responds, confirming it's healthy. A few seconds later, another check, still healthy. Then another, still good. These tiny requests run on a constant loop, and honestly, the people ordering their lunch never even know they're happening. Now, let's break something and watch what happens. Bam! The primary database suddenly crashes. The very next health check goes out, but total silence. No response. A few seconds later, another check is sent. Still nothing. Then another. Silence again. At this exact moment, FoodDash finally has the hard evidence it needs to conclude that the primary database is undeniably down. And this is where the absolute magic of failover kicks in. Failover just means moving traffic away from a broken component over to a healthy one. And we follow an exact automated sequence to do this. First, the system detects the failure. Second, that perfectly synchronized backup database, it's officially promoted to be the new primary. Third, the live traffic is seamlessly redirected over to it. And finally, the application servers reconnect. Just like that, FoodDash keeps running and the food keeps getting delivered. So the crucial point here is what didn't happen. Notice how nobody had to wake up a panicked on-call engineer at 3 a.m., nobody had to manually log into a server, and nobody was frantically typing in new configurations by hand. The system spotted the problem and fixed itself, entirely on its own. That's the real power of automatic failover. But, as engineers, we know real-world systems aren't always quite that perfect. Sometimes a server is just temporarily choking on a heavy query, or maybe a network packet just gets lost in the void. What if a health check fails, but the database is actually totally fine? If FoodDash immediately triggered a massive failover after just one missed check, the entire platform would become incredibly unstable. We call these false positives, when the system gets jumpy and incorrectly assumes something died when it really hasn't. And this brilliantly illustrates why we never, ever trust a single failed check in production. Instead, we use thresholds. We require multiple failed checks over time before taking any drastic action. So a check fails at T0. Okay, wait. Then it fails again at T plus 5 seconds. Then again at T plus 10 seconds. Only after, say, 3 consecutive failed checks do we officially declare that component dead. It's the perfect balance, really. We catch genuine failures fast, but we completely avoid those unnecessary chaotic failovers. Now, here's the cool part. This exact same pattern isn't just for databases. It's used everywhere in modern systems. Let's actually shift our focus up the stack for a second, away from the databases and over to the application servers and load balancers to see how this plays out on the FoodDash backend. Imagine FoodDash has a cluster of 4 backend application servers sitting directly behind a load balancer. Just like before, that load balancer is continuously checking the health of every single machine. Right now, looking at the cluster, all 4 servers are perfectly healthy. They're happily crunching numbers and routing food orders. But suddenly, server 3 completely crashes out. The load balancer immediately spots those failing health checks, and without a single human lifting a finger, it seamlessly removes server 3 from the active rotation. All the new incoming orders are instantly routed to the remaining 3 healthy servers. This is the absolute beauty of load balancing. Customers keep ordering their food, completely oblivious to the fact that a server just died in the background. And better yet, the system is smart enough to heal itself. Let's say server 3 reboots and finally comes back online. The load balancer's health checks start getting successful responses again. It immediately marks the server as healthy and drops it right back into the active rotation. So automatic recovery works flawlessly in both directions. It pulls out the bad, and it seamlessly tags the good right back in. Which leads us to a critical engineering mantra you absolutely have to remember. Never assume failover works. Test it. As engineers, we have to intentionally shut down servers in controlled environments. We actively simulate these complex outages just to validate our recovery mechanisms long before a real incident strikes. Because trust me, the absolute worst time to discover your failover is broken is during a massive production outage at 2 in the morning. So let's quickly summarize this incredible system we built for FoodDash. Redundancy gives us our backup infrastructure. Replication keeps those backups perfectly synchronized. Health checks act as our eyes, continuously watching for failures. Failover seamlessly redirects the traffic. Load balancers automate the recovery on the application side. And of course, rigorous testing ensures the whole shebang actually works when it matters most. Working together, these components let us survive massive failures with basically zero downtime. But there is still one huge underlying question we haven't answered. Sure, we can recover quickly now, but how much downtime is actually acceptable for an app like FoodDash? I mean, how do engineering teams formally measure availability? How do they define exactly how much downtime the business can handle before it becomes a total disaster? Like, what do companies actually mean when they promise 99.9% availability? And why does every extra 9 in that number become exponentially more expensive to achieve? Well, that is exactly what we're going to be breaking down in our next explainer on availability targets and the famous 9s. Thank you so much for joining me for this engineering systems explainer. Make sure you subscribe so you don't miss the next one, and I will see you then.